Question 1. If light strikes the boundary between two media at an angle larger than the critical angle, how does the light refract? Does it bend toward the normal, away from the normal? Does the angle of refraction equal the angle of incidence? Or does the light not refract at all? Let's think about this for a moment. There's a critical angle, then that means that we're going from a material with a high refractive index to a material with a low refractive index. Otherwise, there would not be any critical angle. If we're going from low index to a high index, we can always find an angle of refraction, and so there is no critical angle. So let's go through our options. Is it C, the angle of refraction equals the angle of incidence? This can only happen in two cases, either if the two media have refractive indices that are exactly equal, or we have the incident ray coming in at 0 degrees to the normal. And in this case, we're looking at an angle larger than the critical angle, which will probably not be 0 degrees. If we say A, the refracted light bends towards the normal, then that would mean that we're moving into a material that has a higher refractive index. And we know that if we're moving from a low refractive index into a high refractive index, then we can't get total internal reflection, so there's no critical angle. How about B? The refracted light bends away from the normal. Now normally, this would be the case. We go from a low refractive index into a high refractive index, or rather a high refractive index into a low refractive index, then we'll bend away from the normal. But in this case, we have an angle that's larger than the critical angle, which means that if there were any refracted rays, they would need to have a sign that was greater than 1, which can't exist. This means that we can't get any refracted light. Our last option is D, the light does not refract, and this is indeed the correct answer. If we pass from a material with a high refractive index into a material with a low refractive index, but if we try to pass through at an angle that is greater than the critical angle, then we can't refract, and instead we get total internal reflection. Question 2. If light strikes the boundary between two media at an angle smaller than the critical angle, how does the light refract? So in this case, we might have an angle of incidence that is very close to the normal. Does the refracted light bend toward the normal, away from the normal, neither of these, or does it not refract? Now once again, it can't be A. If there's a critical angle, it means that we're going from a material with a high refractive index into a low refractive index. And that means, of course, we can't bend towards the normal. Instead, we have to bend away from the normal. And so our answer is B, the light refracts just as we would expect it to, as we've been studying in the previous sections. Question 3. Calculate the critical angle of an incident ray passing from water into air. So in this case, the refractive index of water is 1.33 and air is 1.00. Now what we should use here is Snell's law, but we need to set the angle of refraction to exactly 90 degrees, because that will be the very limit of refraction. If we try to refract with an angle of incidence greater than this, we won't get any refraction. At exactly the critical angle, the sine of the refracted angle equals 1. And of course, we can't get it any higher than that. That's the maximum value for sine r. Using Snell's law and rearranging a bit, we end up with this equation here. The sine of the angle of incidence equals n2 over n1, sine of the angle of refraction, which, as you can recall, we've just set to 1. We have the sine of the critical angle is 1.00, that is, our n2, over 1.33, n1. Remember that water is n1 because we start off in the high refractive index and we try to pass into the low refractive index. Rearranging this, we need to set the critical angle to the subject of the equation. We end up with the inverse sine of 1 over 1.33. Now at this point, we'll be able to figure out if we've messed up, because if we put 1.33 over 1.00, then we won't be able to find the inverse sine of it. You can only find the inverse sine of numbers that are between -1 and +1. So finding the inverse sine of this number here gives us 48.75 degrees. That means that if we try to pass from water into air at an angle of incidence greater than this, then there'll be no refraction. Instead, we'll get total internal reflection. Question 4. A certain diamond is found to have a critical angle of just 24.41 degrees when it's surrounded by air. Calculate its refractive index. So gemstones tend to have quite small critical angles, which means that it's very easy for total internal reflection to occur. Now, how do we figure out the answer to this question? Once again, we'll be using Snell's law. In this case, we already know what the critical angle is. We're trying to figure out the N1 and the N2, except we know already that the N2 is going to be that of air. We're going to be using sine of r equals 1. That is, the refracted angle is going to be the maximum refracted angle when we come in with the critical angle as the angle of incidence. The sine of this angle will be the sine of 24.41 degrees, which evaluates to 0.413, right? That's just taking the sine of this angle here. So now we have sine of I and sine of r, which is good if we want to use Snell's law, right? Using Snell's law, we have N1 equals sine r over sine I times N2. N1 is what we're trying to figure out, the refractive index of the diamond. Now all we need to do is substitute the other values. So we have 1 for sine of r, 0.413 for sine I, and 1 for the refractive index of air. Putting this into a calculator, we get a value of 2.42 for the refractive index of a diamond. Question 5. When a gem sparkles, light entering the top of the gem is internally reflected until it exits at the top of the gem. Draw the path of the light rays on these diagrams below to show why gems must be cut into an exact shape for maximum sparkle. Now, here are the diagrams. So you can see that in each case, we have a gem with incoming light from the top, except the gem has been cut in different ways in each diagram. Here it's been cut very shallow, here it's been cut very deep. Now, if we want the maximum sparkle, then we need a lot of light going into the top of the gem. We need to be refracted, or rather internally reflected, until it reaches the top of the gem again. If any of the light refracts and leaves the gem out of the bottom, then the sparkle won't quite be as bright, because we won't have quite as much light coming back out of the top of the gem. Now, in each case, the beam of light is coming down perpendicular to the top of the gem. So the angle of incidence will be 0, the angle of refraction will be 0. So that means that just as the light passes through the surface of the gems, it will stay perpendicular to the surface, that is, parallel to the normal. So the light will start by coming down like this. So now the light will meet the bottom of the gem at an angle. What we need to do is figure out what's going to happen. Will there be total internal reflection? Or will some of the light pass out of the gem? Well, let's take a look at some of the angles involved by drawing the normal on. The normal to the bottom of this gem will look something like this. So you can see that we have quite a small angle inside. The normal to this gem is a bit bigger, or the angle of incidence to the normal. And here, it's very large indeed. So if any of these gems are going to have a beam of light that refracts and passes out of the gem, it's going to have to be the one on the left, because this one has the smallest, or rather the largest angle away from the normal. We'll end up with something looking a bit like this. You can see that for angles larger than the critical angle, these two gems, we get total internal reflection. The light is not refracting out because there's no angle out of which it can refract that will satisfy Snell's law. Only the light with a very small angle is able to refract. So this has only a very small angle to the normal. And this means that even if we get some light reflecting, we won't get that total internal reflection that makes the inside of the gem behave like a mirror. So in this case, we won't get quite as much sparkle as if we had bounced off a mirror, say. All right, now let's look at the other two. Once again, the light has reached one of the boundaries of the gem. Now let's look at the angles here. In this case, the normal will look something like this. And so the angle between the incident ray and the normal will be very, very small, smaller than the critical angle. Here, the angle is much larger, so we're much more likely to get total internal reflection, rather. Remember that gems have very large indices of refraction. Incident rays can totally internally reflect, even if the angle is quite small, although probably not as small as this. So if we were to draw how the light behaves as it reaches the boundary of the gem again, we'll probably get something like this. We can see that the light, as it passes out of this gem, will bend away from the normal because it's passing into a high refractive index. but we won't get total internal reflection because we're too close to being perpendicular to the surface. Here, however, because the angle of incidence is so large and larger than the critical angle, we once again get total internal reflection. The inside of the gem is acting like a mirror. Here we'll probably still get a little bit of reflected light that might bounce out something like this. Except that when this happens, we'll get light lost to refraction, both out of the left and the right of the bottom of the gem. Now finally, we've reached the top of the gem again, and once again we're parallel to the normal. So angle of incidence is 0, angle of refraction is 0. We pass out like this. So this means that almost all of the light coming into the top of the gem is totally internally reflected, unless it's coming in at exactly the wrong angle. You can see that in this middle gem, there is far more light ending up coming out of the top of the gem than in either of the other two cases. And this is what causes the most sparkle. So if we want to have a very, very sparkly gem, then we need to cut it in exactly the right way. So this concludes the questions. Today we've learned a little bit about total internal reflection and how we can see it in the world around us. In the next section, we'll be looking at how we can use total internal reflection to make optical fibers that allow us to transmit large amounts of data very quickly.